Question number 1 is about Schrodinger equation. In this equation, h bar is a constant. It's a Planck constant divided by 2 pi. M is the mass. So if this Schrodinger equation is about an electron, then this M is the mass of the electron. Or if this is about a molecule, then M is the mass of the molecule. Vx, this is the potential energy of the system, and usually potential energy is a function of location x. And so Vx means it depends on position x. And E is the total energy of the system. Psi is called wave function. As we mentioned in class and in my lecture notes, wave function does not have a physical meaning itself, but wave function squared tells you the probability to find the particle in a location x. So next, identify two operators in this equation. So in mathematics, we consider operations using operators. For example, 5 times 6. The 5 times, we can think about this as an operator. So this equals the operator operates on 6. So this operator operates on 10 would be 5 times 10 is 50. So 5 times is an operator. If we look at the Schrodinger equation, potential energy times wave function, and that's an operator, and this is a potential energy operator. So we can write the symbol potential energy operator. So that's a potential energy multiply. And the first one here is the wave function. So everything in front of it, it's an operator. So negative h bar squared divided by 2m. Second derivative is an operator. In fact, in quantum mechanics, this is called kinetic energy operator. So this is a kinetic energy operator. As I mentioned in class, in classical mechanics, kinetic energy can be written as 2m p squared, momentum squared. If you compare these two, they have similarity. One is classical mechanics. In quantum mechanics, it's an operator. That's a second order derivative. So the Schrodinger equation, if we look at these two operators here, operator, potential energy operator, so we can simplify as kinetic energy operator operates on wave function plus potential energy operator operates on function and the wave function times energy. Or you can combine these two together as a total energy operator operates on wave function, give you function back times energy. So this is the Schrodinger, simplified Schrodinger equation. In mathematics, this is called the eigenvalue problem. Operator operates on function, give you function back times a constant. That's the eigenvalue problem. Question number 2 is about the constraints of wave functions. It asks you which of the following wave function would be acceptable as a wave function. As we mentioned in class, wave function squared is related to probability, and therefore wave function cannot be infinite. So cannot be infinite. Wave function must be continuous. And the wave function must be single valued, because every point must only have one probability. And also the fourth one is wave function first order derivative must be continuous, and this is due to the Schrodinger equation, which is a second order differential equation. So first order derivative must be continuous. Now let's look at 4 functions. The first one is x squared. If we plot it, you will see the wave function go to infinity in both ends. And therefore, this function cannot be a wave function, so because it goes to infinity. However, if we confine wave function in a certain range, for example, here from -1 to +1, then this is acceptable as a wave function. If it doesn't have a range, then it is not acceptable. Second question is 1/x. So again, let's plot it. When x goes to infinity, 1 divided by infinity is 0. So it goes to 0 like this. But if x approaches 0, 1 divided by 0 is infinity. So it goes to infinity again at x equals 0. And therefore, this is not acceptable as a wave function because wave function approaches to infinity when x approaches to 0. Unless if you exclude x equals to 0, then it can be a wave function. Okay, next one, e to the negative x squared. If we plot this function, you will see something like this. So this is not infinite function, and it's continuous, it's single valued, and therefore this is acceptable as a wave function. The last one, cosine. So if we plot it, it's oscillate like this. So again, this is a continuous, single valued, and not infinite, and therefore it is acceptable as a wave function. Question number 3 asks you to calculate the probability of this wave function in a certain range. So A is x greater than 0. Now in quantum mechanics, a wave function squared is the probability of a point. If we times delta x, that means this is the probability in the range delta x. If we want to calculate probability in a measurable range, we need to integrate from initial to final, for example, A to B. So the range, a certain range from A to B. So first, to calculate the probability, we write squared, or wave function squared, integration in the range. For A is x equal greater than 0. That means it's from 0 to infinity. That's the range. X is greater or equal to 0. Next, we plug in the wave function into this equation. So we write e to the negative half x squared. So when you square it, the power times 2, and that gives you negative x. So e to the negative x. The integration of e to the negative x is negative e to the negative x from 0 to infinity. Now you plug in the infinity, so e to the negative infinity is the final minus e to the negative 0, initial. So final minus initial. So this one, e to the negative infinity is 1 divided by e infinity. That's 0. So first one is 0, and the second one, e to the 0 power is 1. So that gives you 1. So the probability in this range x greater or equal to 0 is 1. If we plot this wave function, you will see something like this. So it is go from 1 to 0. Okay, so x go from 0 to infinity. The wave function decrease to infinity. The whole range is from 0 to infinity. So we are calculating the whole range, and the probability is 1, and that makes sense. The next question is not the whole range, but x greater or equal to a. A is an arbitrary number, for example 3. So we are asking to calculate from a to infinity this range. What's the probability in this range? And again, we write equation psi squared from, in this case, is from a to infinity. Okay, so we do the same thing. We get negative e to the negative x, but from a to infinity. And that gives you 0 minus e to the negative a. So the answer is e to the negative a power. That would be the probability in the range x greater equal to a. Question number 4. Construct the potential energy operator of a particle. Now in our lecture notes, you will find a slide named frequently used operators. And there you will find that potential energy operator is just potential energy itself. So if you use potential energy operator operates on wave function, it's just the potential energy times wave function. And another one is potential operator. So position operator is just position itself, similar to potential energy operator. Now there's another one, important one is momentum operator. Momentum operator is negative h bar times I times h bar first derivative. So if you use a momentum operator operates on wave function, then you should write IH first derivative of the wave function. Another important one is the kinetic energy operator, which equals negative 2m h bar squared second derivative. Okay, so these are very common used operators. So potential energy operator is just potential energy itself. In this case, it's given half kx squared. So the potential energy operator is half kx squared. Question number 5. Identify which of the following functions are eigenfunctions of operator ddx, the first derivative. In quantum mechanics and in mathematics, a function is an eigenfunction of an operator. That means if you use this operator operates on the function, you will get the function back times a constant. So that's a constant. If this meets the requirements, then you can say this is the eigenfunction of this operator. So now let's use this operator to operate on those functions and see if you get function back times a constant. In A, we use operator, which is first derivative, operates on the function is cosine kx. So first derivative of cosine kx, which is negative sine kx. So negative k times sine k. And this doesn't give cosine back, and therefore this is not a eigenfunction of the operator. Now next one, again we use operator, operates on the wave function. In this case is eikx. So eikx, when you derivative it, you get ik e ikx. And this does give you the function back times a constant ik. Therefore, this function is an eigenfunction. Okay, next one, we do the same. Operator operates on the function. In this case, the function is kx. The derivative of kx is k. It doesn't give the kx back, and therefore this is not eigenfunction. Last one, the function is e to the negative ax squared. So that when you derivative, first derivative, you get e negative ax back, but you also derivative of ax squared give you 2ax. So in this result, not only you have function e to the negative ax, you also have x, which should include as a new function. This new function of x is not simply e I psi, this one, this iax, because you times x, you have x here, So the new function is not the original function. You don't get the function back times a constant, and therefore this is not a eigenfunction. Question number 6. Normalize the following wave function. Now we already know wave function squared represents the probability of a point. If wave function squared times dx integration from a to b, that means this is the probability from a to b in this range. If ab is the whole range, then the probability must be 1, because it's about the probability. If the particle exists in this range, then in the whole range, the probability must be 1. And this is called normalize. Normalization is important because you make the wave function probability equals 1. So sometimes if the wave function has an unknown, you can normalize it so you can find the unknown in the wave function. Now sometimes the wave function doesn't have an unknown. You can still normalize it. You can add an unknown to make the wave function probability equals 1. So let's look at this wave function. Sine L is the length of this range from 0 to L. So that's the length. N is a quantum number. X is the position, is a variable. So this wave function does not have an unknown. To normalize it, you add a unknown, A or B. It's unknown. You solve it so that the wave function becomes normalized. In other words, the probability in the whole range is 1. So in general, when we normalize a function, we write psi squared integration in the whole range equals 1, and then we plug in the wave function. In this case, it's a times sine n pi x over L. We want to find what a is to make this wave function normalized. Okay, so plug in, you square it. Okay, now sine a function's square in mathematics can be written as this: 1 minus cosine 2y over 2. So sine y squared. If we compare ours, its sign, then this m pi x over L is y. All right, and therefore you just replace y by m pi x over L. So you get this equation. And 2 is a number, a is a unknown number, so you can remove or move them all in front of integration. Okay, and only integrate here. One integration is x, so 1 is x, cosine is sine. Okay, so you get this one integrated, and the integration range is from 0 to L. So the last step is plug in L into x, and then plug 0 into x. So use final minus initial. So please try that. Your answer should be L. So the integration here should be L. And therefore, a squared divided by 2 times L should equals to 1. And that indicates a should equals to square root 2 over L. And therefore, the normalized wave function is square root 2 over L times sine n pi x over L. That means this wave function, the probability in the range 0 to L is 1. Question number 7. What is the kinetic energy of a particle described by the wave function cosine kx? In quantum mechanics, if we want to find observable, in this case is kinetic energy, which is observable, you need to use the corresponding operator. So operator operates on the wave function. If you get the function back times a constant, then we say this function is eigenfunction of this operator, and this is the eigenvalue, which is the observable. So if this is a kinetic energy operator, then this will be the kinetic energy of the particle. Okay, so all you need to do is use the operator operates on the wave function and find the eigenvalue. So what is the kinetic energy operator, which as we mentioned before, is negative h bar squared divided by 2m. Second derivative operates on the wave function. So in this case, the wave function is cosine kx. Now cosine kx, the first derivative is negative k times sine kx. And the second derivative should be negative becomes just negative k times sine kx derivative should be k times cosine kx. So this is the second derivative of cosine kx. So it's this one. Now you have a negative sign here, so negative becomes positive, and k times k is k squared. So the result is h bar squared k squared divided by 2m cosine kx. Now cosine kx is the wave function. So if you compare here, you use a kinetic energy operator operates on the wave function, you get the function back times a constant. H bar is a constant, k is a constant, m is the mass, it's constant, and therefore that's the eigenvalue, which is the observable. In this case is the kinetic energy. So kinetic energy is h bar squared k squared 2m. Now if the question is ask you about the momentum, okay, so what is the momentum of this wave function? Then you should use the momentum operator operates on the wave function and see if you get the function back times a constant, which is the eigenvalue. That's the momentum. Question number 8 is to prove wave functions are orthogonal. In quantum mechanics, wave functions of different eigenvalues are orthogonal. An familiar example is about hydrogen atom. So in hydrogen atom, there's different wave functions. So we know 1s orbital, 2s orbital, and go on. These wave functions are orthogonal. In quantum mechanics, orthogonal means the two wave functions product is 0. So in this case, for hydrogen atom, we should be able to prove wave function of s orbital conjugate times wave function of 2s orbital integration in the whole range is 0. So that means these two wave functions are orthogonal. Now in this question, the solution for a particle in the length L, this range from 0 to L. So in this range, a box with length L has different wave functions sine n pi x divided by L. N can be 0, 1, 2, no 0, 1, 2, 3, and keep going. So the first wave function is sine pi x divided by L, and the second one is sine 2 pi x divided by L, and then 3 is when n equals 3. So you have an infinite number of solutions. Just like hydrogen atom, you have 1s orbital, 2s orbital, 2p orbital, and keep going. So many wave functions. These are all orthogonal. Same things here. So we are going to prove psi 1, psi 2 are orthogonal. So all we need to do is to plug in the wave function into this equation, okay, and prove the product integration is 0. So here is the wave function. The first one is sine pi x over L conjugate times second wave function, 2 pi x over L. Okay, now because these are all real numbers, so the conjugate is just itself. Okay, so it's just the sine pi x over L sine 2 pi x over L. Now we have this equation. If two sine function product, it should equals to this equation, have cosine A minus B minus cosine A plus B. So using this equation, okay, we can calculate this product equals cosine pi x over L minus 2 pi x over L minus cosine pi x over L plus 2 pi x over L. Simplify this equation. We get cosine pi x over L minus cosine 3 pi x over L. The integration of cosine is sine, so we have this equation, sine pi x over L, but you need to times L divide by pi to get the derivative will be cosine pi over L times x. Similarly, the integration of cosine 3 pi over Lx equals L divided by 3 pi sine 3 pi x over L. Don't forget, this is integration from 0 to L. So all we need to do now is plug in L to replace x by L, and then minus the function when x is 0. So you should be able to prove that this is 0. Okay, so please try yourself and see if this is 0. So if this is 0, that means that this product integration is 0. In quantum mechanics, that means these two functions are orthogonal. Question number 9. Calculate the average value of the position of electron in the second lowest energy level. The wave function is given here. Now, in the last question, we also mentioned 1D box model, and there's a solution with n equals 1, 2, 3, 4. Okay, just like hydrogen atom 1s, 2s. So you may wonder how do they come from? Well, later in the future we'll show you these are the solutions of Schrödinger equation. So right now just accept these are the wave functions, just like hydrogen atom 1s orbital, 2s orbitals. And here we only choose n equals 2, and we want to find the average value. Now average value in quantum mechanics is also called the expectation value. So in our lecture notes, you will see a slide titled expectation value. And the equation to calculate expectation value is the wave function conjugate times operator, and then times the wave function integration in the whole range. That is how you calculate average value or expectation value of a normalized function. If it's not normalized, you also need to divide by integration wave function conjugate times wave function detour. But if it's normalized, this equals 1. That's normalization, right? So in this case, these functions are all normalized, so you don't need this. Okay, and also note that the expectation value or average value should integration in the whole range. In this case, the range is just from 0 to L. Okay, you need to pay attention to the whole range. So here it's just 0 to L. Okay, so all you need to do, plug in. Also note that we want to calculate the average value of position, and therefore the operator is a position operator. Position operator is just position itself. Okay, that's the wave function. Because it's real number, so the conjugate is just itself, and the position operator is just position. Okay. Now again, if you're asked to calculate the average value of momentum, then you should use momentum operator here. Okay, wave function, momentum operator, and then wave function. And here is the position, so just times x. And then integration in the whole range, in this case, is from 0 to L. Okay, and then the wave sine squared times x, and then in calculus book we'll find a standard integral like this, x times sine kx squared. So this is x times sine squared. So that means 2 pi x divided by L, 2 pi divided by L is k. So k equals 2 pi divided by L if you compare this to the standard integral. So you replace here k by 2 pi over L, you should get the result here. Okay, so you should get this equation. And then simplify this, you should get L over 2. Okay, now this wave function, if you plot it, the box L, so if you plot it, you should see something like this one. So it's a wave like this one. The center is 0. So there's no possible you find the electron in the center. The most probable place is here, half quarter L, and this is 3 over 4 L. So this is the most probable. This is also most probable place, because you need to square the function to get the probability. So square like this. So these two are most probable place. Okay, but every time when you measure it, it could be here, or possibly any place else except center or these two ends. Okay, but in average, if you measure a lot of times, average is actually in the center, because these two are equal possibility. So it's a symmetric, anywhere symmetric. So that means if a very large number of measurements are made, then the mean value will be at the center of the box. Question number 10. Estimate the minimum uncertainty in speed of an electron in 1D range of length 2a0. So in our lecture notes, as you will see Heisenberg uncertainty principle, which says that momentum position cannot be simultaneously specified with arbitrary precision. The equation is like this. This is momentum uncertainty. This is position uncertainty. The product is always greater than Planck constant, h bar, divided by 2. So in this question, it says that you have an electron in a 1D range 2a0. So this is the length, and we know the electrons inside this range, and therefore we don't know where is it. So this is the delta x, the uncertainty of the position. It can be anywhere, and the length is 2a0. So that's the uncertainty of delta x. A0 is 52.9 pm. Okay, so we know delta x, the electron in this box somewhere, and we want to know the uncertainty of the speed. Okay, the speed is related to momentum. Momentum is m times v. In this case, we times delta v. So delta p is m delta v, and therefore we can calculate delta v equals Planck constant h bar, which is h divided by 2 pi, divided by 2m time and delta x. M is the mass of the electron, delta x is uncertainty of the position. So plug in, that's the h bar, and that's the mass of the electron, that's 2a0, and that is the uncertainty of the electron. And the result is 5 times 5 times 10 to the 5th power meter per second. So the uncertainty of that electron in this very tiny box is very large. If we know the electron in a small range like this, A0 is a very small number, right? So if electron, we know it's inside a small box, okay, then we don't know much about the speed. The uncertainty is a huge number.